Before we can investigate the effect of distance between two charges on the force that they exert on one another, we first need to understand some terms. Remember that inverse proportion means that as the independent variable is increased, the dependent variable decreases by the same factor. For example, the independent variable might increase 1, 2, 3, 4, 5, and the dependent variable that corresponds to that decreases 5, 2,5, 1,67, 1,25, 1. So when the independent variable is low, for example 1, the dependent variable is high, for example 5. When the independent variable is high, for example 5, the dependent variable is low, for example 1. And the rate at which they change is the same. An easy way to recognize inverse proportion is that if you multiply the independent and dependent variables by one another, you get a constant. In this particular data that I've got here, the constant happens to be 5. 5 times 1 equals 5, 4 times 1,25 equals 5, 3 times 1,67 equals 5, 2 times 2,5 equals 5, and 1 times 5 equals 5. When you plot the dependent against the independent variable for inverse proportion, you get a graph like this. We can represent inverse proportion mathematically as shown here. This is the proportion sign. Inverse means 1 over. So x is proportional to 1 over y, or y is proportional to 1 over x. When we say these in words, we would say y is inversely proportional to x. And in fact, that's the same as saying y is directly proportional to the inverse of x. Let's show that in numbers. So here again we have that data I was referring to before. 1, 2, 3, 4, 5 for the independent variable, and the corresponding dependent variable values are 5, 2,5, 1,67, 1,25, and 1. But what about taking the inverse of those dependent variable values? So the inverse of 1 is still 1, but the inverse of 1,25 is 0,8. How do we get that? 1 divided by 1,25 equals 0,8. 1 divided by 1,67 equals 0,6. The inverse of 2,5 is 1 divided by 2,5. It's equal to 0,4. And the inverse of 5 is 1 divided by 5 equals 0,2. And by eye you can see that these two sets of numbers are directly proportional to one another. In other words, x and 1 over y are directly proportional to one another. As x is increased from 1 to 5, 1 over y increases from 0,2 to 1. And this is by the same factor, because look, as we increase x from 1 to 2, that's a doubling. 1 times 2 equals 2. 1 over y is also doubling. 0,2 times 2 equals 0,4. So if we say that x is inversely proportional to y, we are also saying x is directly proportional to 1 over y. Remember that in direct proportion, as the independent variable is increased, the dependent variable increases also, and the rate of increase is the same for both of them. So for example, you might have 5, 10, 15, 20, 25. The independent variable is being increased from 5 to 25, and the dependent variable values may be 1, 2, 3, 4, 5. So you can see as the independent variable increases, the corresponding dependent variable also increases, and the rate at which the increase happens is the same. From 5 to 10 it's a doubling, from 1 to 2 it's a doubling, and so on. We can recognize direct proportion by dividing one by the other, and we get a constant. For this particular data we have here, if you divide independent variable by dependent variable, you always get the constant 5. 25 divided by 5 equals 5. 20 divided by 4 equals 5. 15 divided by 3 equals 5. 10 divided by 2 equals 5. And 5 divided by 1 equals 5. But now it's important to realize that we could do it the other way round as well. You see here, all I've done is I've swapped the dependent and independent so that I've got the dependent first and the independent second, because now I want to divide the dependent by the independent. And you will see you still get a constant, not the same constant as what you got when you did it the other way around, but still a constant. 5 divided by 25, what does it give you? 0,2. 4 divided by 20, 0,2. 3 divided by 15, 0,2. 2 divided by 10, 0,2. 1 divided by 5, 0,2. So it doesn't matter whether you divide the independent by the dependent or the dependent by the independent. Either way round gives you a certain constant, not the same constant whether you choose one way or the other, but still a constant within that set of data. And you just need a constant to diagnose that indeed we have direct proportion here. The last thing we need to understand before we can continue is the inverse square rule. There are many variables that are related to distance by the inverse square. To understand this, let's imagine that we have a spray can of paint. Here at the source we have a spray can of paint, and we press down on the spray can so that the paint sprays out of the can. Now we want to spray a wall. Now it's important to realize that the paint comes from the spray can, spreading outwards away from one point, from the nozzle of the spray can. It doesn't all go out straight. It spreads out in all directions. Upwards, to the right, to the left, downwards, all directions it spreads out. So you can visualize the path of the paint droplets as a cone coming out from the source with the point of the cone at the source and spreading out in 3 dimensions from that source, getting wider and wider. Now, if you have a surface right at the nozzle of the spray can, then all of the paint that's sprayed out will come on a concentrated area on the surface that you place near to the nozzle. But the further away that you place that surface, the less thick any one part of the surface will be covered with spray in a certain time. The fainter the color of the paint will be after a certain time, because the paint has spread out more. The further away from the nozzle, the more the spreading out effect. And it's not linear, this relationship, because of the 3-dimensional nature of the spreading out. What do I mean by it's not linear? Let's say we have a surface and we place it at distance x from the spray can, maybe 1 meter, and we spray the paint for 5 minutes. Then we look at how dark the paint is on that wall, and let's call that darkness 1. Then we take another clean wall or whatever surface, and now we place it at 2x from the spray can. We could maybe say 2 meters from the spray can. And again, we spray for 5 minutes. You see, now the surface is double as far as it was in the first situation. Obviously, it's got a bigger area for the spray to have to cover. So after 5 minutes, it's not going to be as dark as the surface at 1 meter at x would have been after 5 minutes, because the paint is spread over a bigger area now than it was for the surface at x distance. But how much dimmer is this layer of paint going to be after 5 minutes than it was at x? It's double the distance. So is the color going to be half as bright? Is the paint going to be half as thick? No. Not half, but a quarter. Why a quarter? Because by doubling the distance, you have increased the area that intersects the cone radiating out from the spray can 4-fold. You've increased that area 2 squared. You've doubled the distance. You've increased the distance 2 times. But because it's a 2-dimensional space that the surface is occupying, the area has increased 2 squared times. And so the paint is spread over 4 times as much space. And so at each point, it's a quarter as thick as what it was at distance x. So let's pretend we take that surface away, and now we put a surface, maybe a wall, at 3x, maybe 3 meters, we could say. And again, we press down on our spray can for 5 minutes. Can you see, by making the distance 3x, the area that falls within the cone of the spray paint spreading out is now increased to 9 times more than it was in the first situation. The area is 3 times 3 squared, which is equal to 9. And therefore, the thickness of the paint after 5 minutes will be 1/9 of what it was at distance x. And at distance 4x, the area that the paint has to cover now is 4 times 4, 4 squared, compared to the first situation. And so the thickness of the paint after 5 minutes will be 1/16 of what it was for distance x. And this is called the inverse square rule. Inverse because the further away from the source, the weaker the impact. In this case, the impact is how thick the paint is at every point within the wall. So the further you place the wall from the source, the thinner and thinner that layer of paint becomes. It could instead be gravitational force or electrostatic force. The further two charges are away from one another, the less the force between them. That's why it's inverse. The more the distance, the less the effect, whatever that effect may be, probably the force between two things. But it's not linear, it's by the square. If it were linear, if you double the distance from x to 2x, that should halve the effect from 1 to a half. But it's not linear, it's by the inverse square. Doubling the distance from 1x to 2x causes a decrease in the effect by the square, from 1 to 1 over 2 squared, a quarter. Tripling the distance from x to 3x decreases the effect by 3 squared, from 1 to 1 over 3 squared, 1/9. Increasing the distance from x to 4x decreases the effect from 1 to 1 over 4 squared, 1 over 16. So as we investigate the effect of distance on force, bear in mind that we're probably going to find the inverse square law applying.